Okay, this is Dr. Kraus recording a video to help my students get started with pulse width modulation, or PWM, and specifically to get them ready for the Friday lab. So what I've done is downloaded the first PWM file that I'm going to provide you with, Arduino-wise. It's pretty short, and it doesn't do a ton. It sets up PWM, it sets up a 50% duty cycle on pin 6. You're going to want to change this line. If most of you have a mega, so you'll want to uncomment this line like so, and do that if you have a mega, or do the opposite if you have an Uno. So pin 4 for mega, pin 6 for Uno. That has to do with the PWM timers and where timer 0, which pin that controls. Then all it does after turning on serial and turning on the PWM is wait for a serial character. It's looking for an ASCII 1 through 5, then subtracting an ASCII 0 to get us a value of 1 through 5, and then it's setting the prescale value, which you'll see in your lab handout, to that 1 through 5 value. So 1 is super fast, probably 16 megahertz with a prescale of 1. 5 is the opposite extreme, prescale of 1024, and so your overall PWM frequency is 16 million divided by 1024 divided by 256. So when you first turn it on, you're going to see something. If you try to record it in lab, you're going to see something crazy fast because it's trying to do that 16 megahertz. So probably the first thing you want to do is launch your serial monitor and just type a 5. And that'll drop it down into a reasonable frequency. I'll show you my oscilloscope in just a second. So over here on the Uno, I've got a wire coming out of 6, which is my PWM. I've got a wire coming out of ground. That's going into an RC filter. So this is 6 going into the resistor. Here's the capacitor connected to the middle point, and the capacitor comes back to ground. So on my oscilloscope, I'm measuring the PWM input voltage, which is the input to the RC filter, and then I'm measuring V out across the capacitor, like so. I'll try to pan now. Okay, so this is the PWM is the green, the square wave at the low frequency. So this is a 60 hertz input square wave that's on 50% of the time. And then the filtered is the yellow. And so the main idea behind PWM is that your square wave would be going super fast, and then your RC filter or your motor or whatever would not really be able to respond to that, but would respond to kind of the average value. And so as you vary the on percentage, you change the DC value. So this is an example of just going too slow. And then one of the things I want you to do is to then come into this serial monitor. So if I enter a 4 into my serial monitor, what just happened is that I now have a 244 hertz input wave, and you can see that the RC filter doesn't quite get all the way to steady state, either when it's on or when it's off. Now what we're expecting, because this is a 50% duty cycle, if this were a fast PWM frequency, our expected output value would just be halfway in between the two. So 2.5 volts is, I think, what we would expect coming out of the Arduino. So if I then come in and put a serial of 3, that doesn't seem to have responded. Whoops, maybe I skipped over 4. I'm having a disagreement with my oscilloscope. Take 2 on the serial stuff. Using the serial monitor to control the PWM frequency. I think my oscilloscope is just having a triggering problem. If I force some triggers, I think I can make good things happen. So what I want you to see is when I send a serial of 5, that sets it to the slowest PWM frequency, which is apparently 60 hertz. And we see the green square wave here that's 50% duty cycle, 5 volts. The yellow is the filtered RC circuit response, which we would want to be relatively flat or constant, ideally in this situation. And like I said, we expect a duty cycle of 50% to lead to a average value 2.5. Sorry, I'm just messing with the focus. So here I am. send a 5, get this output. So then if I change it to 4, I'm changing the prescaler, and now my PWM signal got faster. So if you're looking at the time scale is getting slower or smaller on the oscilloscope, and it's measuring a frequency of 244 hertz. So I think I just used a factor of, I guess, 6. That seems a little weird. And then we changed the prescaler from 1024 to 256. No, I guess it's a factor of 4. Sorry, bad math. Okay. So here we are at 244 hertz, or prescaler of 256, I think. And then if I send it a serial of 3, my trigger's better behaved. Now I got to go zoom in a little bit more on my horizontal axis. And now I've dumped my prescaler from 256, I think, down to 64. And so now I'm at just under 1 kilohertz, 973 hertz. And you can start to see that the filtered output amplitude is obviously going down as we go higher and higher in frequency. If you think about where we are on a Bode plot, which I'm going to ask you to generate, we're now above the corner frequency, and so we start to see that amplitude attenuate. If I go to a serial of 2, I may have to force a trigger. There we go. And now the PWM frequency is 7.8 kilohertz, and you can see the peak-to-peak ripple on the output. The output is getting to that flat 2.5 volts that we would expect as the peak gets smaller and smaller. And then in the limiting scale, and this one you won't be able to do on the LabVIEW stuff as far as measuring the input, because it's just too fast. This is a 124 kilohertz input square wave, and your devices, I think, peak out at 50 or 100 kilohertz, so we would definitely have aliasing problems, so on and so forth. I mean, you can start to see that now we really have achieved a flat 2.5 volts pretty much on the output. There's some little high frequency noise things going on. But yeah, as I'm varying the input square wave frequency of the PWM, the output amplitude is changing. And so what we're going to do for the rest of the lab is run things at 7.8 kilohertz, because that's something that you guys can handle with the equipment that you have. And the ripple is what I'm going to call just kind of acceptable. I don't know why that's not reading correctly, but that's the 7.8 kilohertz square wave frequency that you'll use with a serial of 2. So prescaler set to 2, which turns into an 8 in the conversions. Yeah. So the next video I'm going to record, next part of this video, I will then vary the duty cycle, and we'll see how the DC value changes. Okay, this is Dr. Krause with one more quick recording. I've written a new Arduino file that I'm calling Pwm Duty Cycle.eno, and I'll make this available to you as well. It's pretty similar in some ways to the other simple one. The difference being I've hard-coded the prescaler value to be a 2. So we're going to be operating at the 7.8 kilohertz. Then I've created 2 new values: duty cycle, which is what we'll actually send to the PWM, and that'll be a number between 0 and 255. And then input value, which is the number you're going to send over serial. So now it's accepting digits from 0 to 9 via serial. And then it's subtracting the ASCII of 0 from that to actually convert them into the integers from 0 to 9. And then the duty cycle is going to be that value times 25. So that'll get us values from 0 up to, I guess, 225. And then we're going to send that as our analog write. So let's do a quick, so right now over here on the serial monitor, I have set a 0. I'm going to force a trigger of my oscilloscope, and it's going to show us nothing because we're at 0% duty cycle. I give it a 1, which should set our duty cycle up to 25 out of 255, so 10%-ish. And you can see that the percentage of on time versus off time, it's on about 1/10 of the time. And you can see that the DC off, or the DC value of the output is, I guess, roughly 1/10 of the input. And then if I increase that to a 2 instead of a 1, we're now up to, I guess, 20% of the output. and you can see that the on time doubled and the off time went down by 1 chunk. And sometimes I'm just not getting that trigger, so I'm going to force a trigger. This is now, I've sent a 3 over the serial, and so that leaves us on at roughly 30%, off at roughly 70%, and the output amplitude is roughly 30%. And so I can keep walking my way up, and so this should be roughly 50%. I should set up the measurement of the output average, whatever. And so there's a 60, a 70, and so like we're on 70%, we're off 30%, and our output amplitude is roughly 70% of the 5 volts. And now we're on for 80% and off for 20, and we're at about 80% of the final value. And there I've sent it a 9, and so it's on for roughly 90%, off for 10%, and the final value should be roughly 90% of 5 volts. So hopefully that makes sense and helps you get started with the lab, and then let Greg or I know if there are questions. Thanks.